week to get set up on. Of course, I have particular interest in this problem. I actually did my first postdoc on this thing. This thing is Conway's Game of Life, and I was doing a computer modeling of the brain, perhaps 20 or 30 years ago, and we started with cellular automata like this, which it turns out are a really terrible way to model the brain, but we didn't know that. Anyway, so this is Conway's Game of Life, and it was invented to sort of be like the way mold grows in a petri dish, was the idea. So you just have an infinite grid of squares, and the rule is some of these cells are alive, where the pounds are, and some of them are dead, where the dots are. And the A is a dead cell I just marked so I could refer to it later. So if a live cell, you have time passing in ticks. So you start with this state, and then you go to the next moment of time. And at the next moment of time, you calculate which of the cells are alive or dead. If it's live, if it has fewer than 2 neighbors, it dies. It's too lonely. So this one here is going to die. It only has 1 neighbor. For neighbors, you count the cells that are 1 move away, horizontally or diagonally. So there are 8 neighbors. This cell here has these 8 neighbors. These 3 on top, these 3 on the bottom, the one marked A and the one marked pound. So this cell has 3, 4, 5 neighbors. This cell only has 1 living neighbor. And so the rule is if you have less than 2 neighbors, you die. So this one is going to die in the next thing. A cell with 2 or 3 live neighbors lives. So we can see this one is going to live. It has 3 neighbors. This one is going to live because it has 2 neighbors, and so will this, this one here, this will live because it has 3 neighbors. This one will die because it has only 1 neighbor. That's how it works. And a dead cell will reproduce if it has exactly 3 neighbors. So this one here is going to become alive. Those 3 are enough to make it spread here. And I think it's the only one. This one here only has 2 neighbors. That one only has 2 neighbors. This one has 5. The A has got 3. The A is going to become alive. It has 2 neighbors here and 3 there. So you see how the game works? That's the plan. Now, when I first tried to do this, I tried to model the space with a whole bunch of cells, literally with the pounds in it, and that turned into be a mess. So I realized that was pretty much a dead alley. So I think it was a whole lot better is to just make a list of the active cells. And so what I did was I defined coordinates, and thought I put that in the project here someplace. Yeah, in 2 dimensions, you can do it any way you want. In 2 dimensions, you can even make it like a checkerboard and keep track of every cell. That one's pretty simple. But the fun part is you go to higher dimensions. So obeying these rules in 2 dimensions is really just a matter of a couple of for loops. For x equals 0 to 10, for y equals 0 to 10, go to each cell, check the nearest neighbor. Now, I should mention this because I saw some people are not using for loops, and I certainly would. Howard, let me start you off on what I think is the right track. I would let's just clear this out. All right. And I'll run it this way to clear the answer. All right, so here's what I would do. I would start by making a list to define the initial state. So here, let's call this 0 to 8 and this 0 to 8 or something like that. And you have to play with that. But I just need to say alive equals a list. And the list is going to be of tuples. So let's just count them from the corner, 0, 1, 2, and 0, 1, 2. Okay, cell 2, 2 is alive. So I put 2, 2. I make a tuple there. This is how I did it, and I think it's pretty good. So then 2, 2 is alive, and 3, 2, and 4, 2 are alive. All right, and the one above 4, 2 is 4, 3. And the one up here is 4, 4, and that's 3, 4. So 3, 4 is the last one that's alive. All right, now there are several things you need to do once you have this. One thing you need to do is have some algorithm to execute a time where things change, but another thing you have to do is print out this grid so you can see if you're getting it right. So I define functions for those. Let's make the print grid. So if I define print grid of, say, alive, then I can say, this is where I say for loops are very helpful. So the size of my grid is going to be 8. I'll just make that a variable. And then I'm going to have, now another thing that's annoying is this y prints going down. This is high y, low, 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 and it prints in that order. So I have to do for x in range of size. But I need y to go backwards. So I'm going to do for y in range size minus 1 minus 1. I think that'll do it. It's begin, end, step, and it does not include the end. So this will count from the maximum size down to 0. And now I want to print the cells there. So first I'm going to just print a letter here, and you'll see what a mess it makes. All right, so if I do this, I'm going to get a mess. Oh, and so down here I'm going to have to print, let's call that print grid sub alive. All right, so if I do that, now I just get all these X's down here. That's getting me nowhere. I'm going to need to do something smarter than this. Now, one way to put them on a row is to specify the end mark here. End equals that. That will put nothing at the end instead of a carriage return. So when you do that, now they're all going to be this way. So you still haven't got what you want. So the way to make a reasonable grid is to use a string variable, like row equals string. And now I'll have row plus equals x. Now I'll get something resembling a grid. Oh, and then I'm going to have to print the row somewhere. After each y row, now I print the row. All right. Okay, now I'm getting the grid. Now I just have to fill in the contents correctly. Instead of always adding row plus equals x, I have to say if. I want to see if it's alive. So how do I tell if it's alive? And actually the AI has guessed it correctly here. If xy is a tuple, if it's in this list, then it's alive. And if it's alive, then put a pound there. Otherwise, put a dot there. And now I think I'll get the right grid. However, expect an indentation is wrong. It is wrong. I have to indent this. There we go. All right. So now we get the grid, and you can see if I got it right, and you can see I got it wrong. These are not quite right. That's why the first thing I want to do is print it out. So what did I do wrong? 0, 1, 2, 1, 2, 2, 2 is alive, and x, 3, 2, and 4, 2 are alive, but they don't show up correctly here. I think that's because, x, y, if you think about it, y, you do go through all values of x before you go to the next value of y. These are in the wrong order. This row is supposed to be at constant y, not at constant x. So I've got it, but it's tilted to 90 degrees. Yeah?
Can you briefly explain how you get the numbers and all that?
I'm just counting from here to here. 0, 1, 2, 3, and 0, 1, 2, 3. That's how I did it. Now, you could do it any different way, but that's how I start. Good? And so now the problem is when it prints from top down and to the right. So it prints, I want a row of constant x. I want a row all the same y, but with x going up. So I need to flip these two for loops. I need to put this one first. And this one has to be down there and indented correctly. And that, I think, will be better. Let's see how that looks. Now I'm getting the right shape for starting condition. And by the way, one thing that I think is pretty handy here, I would like to have those numbers on there. So I think I'm going to, instead of starting row at blank, I'm going to start it with y, string sub y, plus, say, maybe a colon and a space. Let's see, that might make it look better. Now I got a number there. I can see the y, and I could even put numbers down there and get me better. All right, so now I'm ready. And that should give you a start. This is a way to get started. Then you need to make a way. Now, the interesting thing about this is when you run this, you could wonder what makes this what controls the efficiency of this process? And what controls one big thing that controls the efficiency is this statement. Think about what this is doing, especially when I start having a lot of living cells. This is looking to see if that tuple is in this list of living cells, but they're not in order. So it's doing a brute force search. So this is going to scale as n, where n is the number of living cells, and that is going to be a problem. So if you go on, the first one here, you just learn how to duplicate this, and this is fine. I should mention parenthetically, if it hits the edge, you're going to have a problem. It's going to try to grow off the edge, and you don't have enough cells there, so you have to make your board big enough to include all the cycles you're going to simulate. It can only move by 1 per cycle. So if you have 6 cycles, you need to have enough to move 6 in every direction, and then you're safe. So first thing is get here, and you get the 4th cycle, but now you extend it to 3 dimensions. So your starting condition is at the plane z equals 0. You start with the same condition, but after the 1 cycle, it's going to spread to the layer below and the layer above. So z equals 0 will be the same as it was before. If you go up here and look at the 2-dimensional game of life, this thing looks like a V turned into this thing. It looks sort of like a lopsided 4, a backwards 4, after 1 cycle. And that is, of course, still true here. This thing will look like a V turned into this lopsided 4, because that plane, at first, all your stuff is in a plane, but it's also grown into the layer below and the layer above. And after 2 cycles, it will grow into 2 layers below and 2 layers above. So it will spread out in 3 dimensions. And therefore, it gets more complicated, and you can count the total active, 21 after 2 cycles, and 38 after 3 cycles. And after 6 cycles, there are 112 living cubes. And I must say, that held me up for a day. I couldn't get 112 because I had indentation wrong. But anyway, let me just point out, to count the neighbors here, you need a lot of loops. Let me demonstrate a bit of the 2-dimensional step here. So for when you grow, if I wanted to count neighbors, let's define grow of alive. Right, what you're going to have to do is you're going to have new alive is going to be a new list. And now I'm going to have y go through all the ranges and x go through all the ranges. I'm going to have another one for dx equals 0, 1, minus 1, which will try this row, and then the same thing for dy. There. This is the kind of thing you'll have. You'll have 4 loops, all indented. The x and y are the cell you're trying to determine if it's going to live. Now you have to got all its neighbors, which is +1 and -1 in x and y. And that's these 2 loops. And then you don't count it itself, and now you can decide, you can count all the nearest neighbors. You're going to have to make some variable to count how many nearest neighbors there are, and then implement these rules back there. If it's 2 or 3 neighbors and it's alive, it lives. If it's dead, it needs 3 neighbors, and then it grows. You have to do that. And so for the 2-dimensional case, you have 4 nested for loops. For the 3-dimensional case, you're going to have 6 nested for loops. And for the 4-dimensional case, you're going to have 8 nested for loops. So that means it's going to do this a lot of times. It's going to be trying to decide if this cell is alive. This step is going to happen a lot. And right now, it's a very inefficient step. It is searching through an unordered list, which is a brute force search that grows with the size of the list. So that's a problem. So you start with a more complex starting place in 2 dimensions. So you go to 3 dimensions and do these, and they'll work. You can do these even with that simple technique. And here, all right. But in the 4th dimension, it's going to get pretty nasty. In the 4th dimension, you have 80 neighbors. There are 81. You have 3 times 3 times 3 times 3. That's 9 times 9. There are 81 cells in the hypercube. And 1 is the 1 itself, so there are 80 neighbors. And so what I did was first I implemented the brute force case. And here's what I found. Starting from that, you have 29 cells, 60 cells, 320, 188, 1056, 848, 3348. And here's how long it took. And you can see it scaling. 5 seconds to do this one. This up first is the one below it. 5 seconds, took 60. Wait, I got it right. There are 29. Took 11 seconds. 60 took 18 seconds. That's doubling it. This is multiplying by about 5. So it goes up from 89 up to 79. You can see it gets up to a really big number. 1056 is 200 seconds. This is 794 seconds, about 10 minutes to calculate that one step at the 8th cycle. So the brute force search is pretty nasty. So you can do it this way. And I gave you a flag which you can still do with the brute force search here. So you only go to the 4th cycle. But for a more complex case, you got to improve it to use a binary search, which means you sort the list and you use an efficient search that won't grow so fast, and then you can get up to the 10th cycle. And here's what I got with my more efficient search. And notice that before, these different layers, the time varied immensely, from 5 up to 80, up to 300, up to 800. This is bad. This is scaling very badly as the problem size increases. But now that I'm using a binary search, it hardly changes at all. It goes from 80 to 116 to 150 to 180. Doesn't do hardly any more than double, even over this huge range of values. So that's the advantage of a binary search. It's growing as log n. Now there is a more efficient procedure called a Bloom filter, which I'm planning to add in later ones, which would not grow at all. The difficulty of determining whether an element is in a list does not depend on the size of the list at all, which is pretty awesome, but log n is already very good. So, and you'll never be able to get to the 10th cycle without improving your list. That was the idea here. I took like 15 minutes or 20 minutes to do it, and I could only get to, I think, the 8th cycle. And Google Colab will time out on you after about an hour and a half. So now you could, of course, run it on a faster machine and might be able to get somewhere, but the better thing is just write a more efficient algorithm with a binary search. And that's the point of that. Let me take a look at the comments here. Okay, no other comments. All right. So I think I'm going to stop the recording. That's all.